Hey, welcome back for OS12 basic keyboard driver and also a discussion of x86 interrupts from PageKey Solutions. A bit of a longer video today, but it will be worth it once you see what you can build. Couldn't have made this video without all of the great resources that people have put together and made available for free online. There's Arjun Sridharan, author of MKey Kernel, which this lesson's heavily based off of. There's the OS Discord community, which they're a helpful bunch for sure, as well as everyone on Stack Overflow, especially Michael Petch, who answered my question in record time. So what are the topics that we need to understand to create our keyboard driver? We'll have to talk about interrupts, the interrupt descriptor table, PICs, or programmable interrupt chips, accessing I/O memory, and some of the mistakes that I made and Michael Petch helped me fix. So what is an interrupt? Here is a definition from osdev.org. It is a signal from a device such as the keyboard to the CPU, telling it to immediately stop whatever it is currently doing and do something else. On this slide we can see why this might be helpful. If we want to interact with the system other than just printing things and having outputs, how do we interpret the inputs from the user? This could be keyboard, this could be network inputs, this could be the mouse. Something's happening external to our operating system, external to the processor. How do we figure out what happened? Well, we can just check a certain memory location and see if it changed since the last time we looked at it. I think some architectures work this way. There actually are no interrupts. You just have to do everything through memory mapped I/O. In our case, we can do interrupts with x86, which is kind of an event-driven flow, where along the top there on the right-hand side, you'll see we're doing whatever. We're chillaxing, we're doing our main program. And then when we have an interrupt that we know that we need to handle, the CPU will stop what it's doing in our main program and execute the handler that we tell it to run. On the left there, I would just say that, in my opinion, it's pretty inflexible and a single thread, so it can be hard to get started with our operating system without these interrupts. So I'm really excited to see how we can start using them. First off, though, here's a quick table. You might want to take a screenshot or something like that of data types and their sizes in C. And I highlighted the 32-bit column because that's all we'll need for today. So the interrupt descriptor table, what is it? Why do we need it? It is a special data structure, and the CPU actually has a dedicated register for this data structure called the IDTR register, and it keeps track of interrupt routines that the CPU should jump to for each type of interrupt. So the IDTR register holds that little table you see on the right, the IDT pointer, which has the limit and the base of our interrupt descriptor table. And then on the right-hand side, you'll see what an IDT entry in that table looks like. You'll see two offset fields. These are split into different parts of the same data structure. When you put them together, it forms the address of the handler routine that we will jump to when we receive this interrupt. The other things, selector, zero, type, attribute, these are all metadata about the interrupt and the interrupt gate, how it should be handled, some of those things. But the big thing for the IDT entry is definitely the offset, which is the memory location where we need to jump when we receive that interrupt. So how the heck do we get to the entries in the table using this IDT pointer? So the IDT itself extends from base to base plus limit in memory. At least that's how I interpreted it. So when the CPU has this IDT pointer stored in that register, you think about it, it really has everything it needs to know to access any of those IDT entries from 0 to 255. And note that there are a max of 256 for x86. Think of it this way: if you have the starting address, the base, first of all, you can access number 0 pretty easily. And then really, you just have to multiply the known size of an IDT entry by whichever entry you want to access. So if you multiply by 0, you're just getting entry 0. If you multiply that size by 255, you get the address of where number 255 is. And then the limit just tells you how big is it, where does it end, and that's really all there is to it. Let's also touch on the programmable interrupt chip. PICs receive interrupts on behalf of the CPU. Multiple input devices are connected to the PIC. Its original purpose was to save ports on the CPU. It's really a legacy chip and is now integrated into the CPU as the APIC, Advanced Programmable Interrupt Chip. The bottom line for the PIC is it can mask interrupts, queue interrupts until it's ready to handle them, and a lot more. It has a whole bunch of features for handling these interrupts. We can mask them, turn interrupts on and off, and if you have interrupts turned off and the PIC is there, it's going to hold on to those interrupts until you turn them back on so that you don't lose any interrupts. Basically, it's kind of our little interrupt guru, separate from the main CPU. So we'll program this using I/O ports, which will lead to our discussion of what is I/O memory, how do we change I/O memory using those I/O ports, and the like. But first, let's talk about how the picks are initialized. It is a preset procedure that you go through, and you're going to send ICWs, initialization control words, to the pick I/O ports. And on the left, you'll see that pick 1 and pick 2 both have their own dedicated command and data ports to receive these ICWs on. And there are 4 ICWs that we need to worry about. The first one is the initialization/reset command to get it ready to receive the other 3. And really we're just sending 0x11, a special value, to the command port on each pick to reset it. Then we have number 2, the vector offset. And this is saying where is IRQ0 on the pick? Where is the first interrupt going to be located? We have to remap this because by default it is 0. But interrupts 0 to 32 are reserved for CPU exceptions such as divide by 0, double fault, triple fault, those types of things. So we can't have the CPU exception firing off and then calling our keyboard procedure, basically. After that, we have cascading settings. How are they daisy chained? Because pick 1 is connected to pick 2. I think you could probably connect more, pick 3, pick 4, pick 5. ICW3 tells us how this is set up, if it's applicable at all. Number 4 is environment info. I don't really know too much about this. It's pretty vague in most of the things that I read, but we're going to use 0x1, which osdev.org tells us is this: x86, MCS 8085 mode. Sounds good to me. And can't go wrong with 0x1, whatever. So that's the procedure to initialize the picks. We did mention that we'll be sending things to different I/O ports and accessing I/O memory. So what's the deal with that, and how are we going to actually do that with instructions in assembly? So I/O memory is another way of interacting with devices as opposed to just modifying the main memory. You can read and write to memory on devices, and it has a separate address space from main memory. Hence the need for separate commands. I was a little confused at first as to why we can't just use the move command for this, but you'll see that these addresses for I/O memory, while they may intersect with something in the main memory, they're completely separate. It's a separate area that we're referring to in the computer. So here are our 2 commands. This is our hammer and our nail here. This is what we need for I/O memory. We have the in command where we say which register we're going to store it in and the port that we're grabbing the value from. So we're going to go out to 0x3, grab that value and stick it in AL. We also have out where we tell it which destination port we want to write to, give it the register that contains the value that we will be writing. Pretty straightforward. So I found this diagram on Stack Overflow, and this was what really helped this concept click for me. You'll see on the left we have the CPU, and it has a bus that goes to memory and to I/O. And you'll see that they have addresses and values for both, and they're completely separate. There's no shared addresses here. Say 0xB8000 in memory is our start of video memory. You could go to 0xB8000 in I/O memory, and maybe it points to something, but maybe it doesn't. It's a separate mapping completely. What's that mean for us? Well, we've been using the move command this whole time, and we've been accessing the main memory in this center block here, our random access memory. If we're using the in and the out commands, we're actually not touching that part of the computer at all. We are in the I/O memory over here on the right hand side. So hopefully that's a good visual for you too. I also made this little diagram for accessing I/O memory and what's actually going on for you to visualize these 2 commands, because it was tough for me at first. We have our example command from before in AL 0x3, and you'll see on the right here we're going into that I/O memory block on port 0x3, and we're taking that value and storing it in AL. For out, we're taking the AO register. I'm not sure if it's actually in the CPU or whatever, but for our purposes, something logically in the CPU here, we're going to take that value and store it in I/O memory port 0x3, hence commanding that I/O device to do something for us. Okay, well, you can read through this if you want, but essentially I was following mkey kernel, which was super helpful, and I got it all to work with QEMU. I got that working keyboard driver just as I thought, and then I tried burning it to an ISO so I could try it out on a real computer, and it didn't work. Every time I hit a key, it would reset again and again. It just didn't work at all. And then I tried it again, except in QEMU with the ISO. Same problem. Something was up. Scoured the internet. I found one answer by Michael Petch, and it had a ton of suggestions for someone else's kernel. So I put as many of them as I could into mine, but of course I overlooked the actual answer. So I posted my own question to Stack Overflow, actually for the first time ever. Within an hour, Michael Petch comes in and answers and solves my problem. So Thanks, Mike. You're the man. And as it turns out, the solution was to set up your registers because you can't count on Grub to do that for you. So I'll show you how to do that in the code. With that, let's jump in and see how we can build this. Before we get too much further, I want to show off what we'll actually be building today so you can see it and know what we're shooting for. So as always, I will check out OS12 on our repository and I will run it. And we have basically what we had before, but I'm going to start hitting some keys on my keyboard. And how exciting. We have a working keyboard driver. And all it's doing is just printing it right out to the screen, but that's okay. It's a start. So let's figure out how to do this. If you'd like to follow along with the code and type along with me, you can check out OS11 and we'll work our way back to OS12, line by line. Let's start out with the boring stuff and get it out of the way. First and foremost, we have some edits to our Makefile, and a lot of them are just cleanup. As you can see, I added an ISO out variable. I'm also going to do the dreaded copy and paste of our build command and make it a build debug command. And the only difference we'll need here is to add the -g/gdb command to our GCC compiler. What this does is includes debugging symbols in our final executable. This will allow us to debug our program using GDB. I made a mistake. Okay. Along with that, we'll add a debug task, and this is going to run everything just like before. Kernel is kernel out ss ampersand. So this differs from our regular run command because we are hosting a little GDB server and we're stopping QEMU system from booting up until that GDB server connects. And of course we had the ampersand so that it runs in the background. After that, we'll run gdb-x means to run the script gdb init. And that's a file that we have to add. But all in all, this debug script just runs QEMU as normal, but pauses it until GDB can connect, and it launches us right into a GDB debugging session. And the gdb init file, we'll just create that now, .gdb init, is pretty straightforward. You just have to write target remote localhost 1234 and file build/pkos.bin to tell it what's the source file, or what's the executable that we're actually debugging here, so it can load all that symbol information that GDB added. Of course, you don't need to execute this as a script. You could just type this in to GDB once that session launches, but it gets really old after the 5th or 6th time you do it, so it's easier to just have a script here. Next, we're going to look at kernel.asm and see what we need to add, and this is more of showing that I'm really just learning this along the way, and probably not too qualified to teach it, but I'll still go through and try to explain the best I can. So we're going to include our GDT, we'll need it later, and I'll just start out by putting all the globals that we're going to declare that we'll need in our C code. We're going to have a GDT function, IDT function, a keyboard handler. We'll have an IO port in and an IO port out. I gave these names. They're a little longer, but they're very descriptive, which I think helps for the whole learning process. A lot of people just say in B or out B for in byte, out byte, but I like the more descriptive name myself. And then we'll have one external function that we'll be using, that we'll be calling rather, which is handle keyboard interrupt. Okay, what's next? Load GDT. Really easy. We've done this before. All we'll just do is load up our GDT descriptor, which is already declared in gdt.asm, which we just included, and we'll return. Next, we will define load IDT. Similar in that it's straightforward. We're just going to grab the first argument that we're passing from C, and then we're going to load that argument into the IDT register, and then we can return. I also had a quick one for enable interrupts. I can't remember if we still use this. It might have just been for playing around, but it's quick and easy, so let's throw it in there. Okay, we have our keyboard handler. We're going to push everything onto the stack. This CLD thing was one of Mike Petch's suggestions. I forget what it does. It has something to do with calling external C functions and how it sets everything up. Feel free to Google it. And now we have handle keyboard interrupt, which we'll be calling. Pop all the registers back where they were, and iret_d. This is a special command to return from an interrupt. You could also do iret. I don't think it makes much of a difference. Let's keep it there just to see if it does later. So what's happening here? So this keyboard handler, this label is actually the address that we'll put into our IDT. Remember that for later. So the CPU, when it sees a keyboard interrupt, it's going to call this. This is our entry point for handling all keyboard events. And really all we're doing is linking it to our C function, which will do some more sophisticated things with that interrupt, and then we're returning. That's what we needed to know how to call assembly from C from. So IO port in, we're going to grab the first argument. This is going to be our port to read, 16 bits. Then we'll just perform the in command. The value gets stored in the AL register, and by default when you do ret, whatever's in EAX gets returned to C. At least that's how I understood it. So there's nothing else we need to do. We grabbed from the port, which we stored in DX, it was an argument, and we returned. So we'll do IO port out now. Let's put in EDX, the first argument, which is port to write, destination IO port, whatever you want to call it, 16 bits as well. And in EAX, we'll put ESP plus 8. And this is the value to write to the IO port. Then we'll just call the out instruction. Easy as that, and we'll return. Lots of setup for the good stuff in the C code. We do have one more thing to do, and that is to set up our registers. And I'll just say thank you, Mpetch. Again, it's already in the comments, but I'll say it again because he figured this out somehow, and I think it's awesome. So we're going to load our GDT descriptor. I don't think that we actually call this GDT function now that I think of it, but it's nice to have, I guess. You can probably remove that because we do it right here. First things first, we load our GDT. We do a far jump to flush the pipeline or whatever it is, which we had to do to move to protected mode back when we were writing our bootloader, and it really just jumps one line, so it's clearly there just to flush the pipeline for any parallel instructions or whatever is going on in the CPU. Alright, we'll move our data segment into AX, and I guess we're just going to move that into everything. ES, FS, GS, they're all going to have that data segment. Honestly, I don't really know what any of these registers are meant for. And then we'll move our stack space variable. All these data seg and stack space, these are in gdt.asm. So yeah, we're just setting up our registers, and that's that. Again, Googling would probably help you understand this better than I do, but that's what I did. Okay, now for the real beast, which is going to be kernel.c. And I'm just going to go line by line and talk through it the best I can. I'm going to omit a lot of comments. If you want to check the repository on GitHub, it will have some more descriptive comments that I've added. First off, IDT size 256. This is a limitation of x86 as I understand it. You can have up to 256 interrupts that you handle. Then we have kernel code segment offset. I actually just had to redo this clip because I forgot what this was and why it was there. I had to spend a long time looking this up to figure out what the heck this meant. Actually, if you go back and look at our GDT, we did the simplest GDT possible where we have one code segment and one data segment, and I think they overlap. This is referring to that code segment that we defined in the GDT. 0x8, why is it that? Why isn't it 00? 0x0. The answer is the first entry in the GDT is the null segment for error checking. The second segment is at address 0x8. So the second segment is the one that we actually defined, not the null segment. If we check gdt.asm, we can actually see it's right here. gdt underscore code is our label, and here's our code segment. But you'll check out we declared two double words, 32 bits. Hence, 0x8 is the address in bytes of our code segment, quite literally. So there you go. What's next? Lots of exciting constants. IDT interrupt gate 32-bit, and that's 0x8e. I just took this from osdev.org yet again. If you want to see what each of these fields are, there is a comment. Who cares though? It's an interrupt gate. There are different types of gates for the IDT. You can look it up. But for now, I don't care. I just want it to work. Let's do some other constants. This time for the pick. Command port is 0x20. This comes right from that table that we had. And we have IO ports for the keyboard. 60 and port 64 for status. Again, this is a lot of stuff from OSDev Wiki. I don't really know what specifications you could find this in as an ultimate source for this. For now, it works, and that's all I care about. So you got keyboard map.h. We'll get to that soon, and I'll talk about how I actually created this from scratch. There is one available on OSDev, or you could use mine, whatever. It's really just a mapping of the codes for each key that is pressed to an actual character so that we can print them out. Because yes, we are at that level. We are that deep that we have to do that ourselves. So now we're gonna define all those functions that we just created in assembly as external little header lines here. You can see unsigned short is the 16-bit arguments that we had. I know I'm making spelling mistakes as I go, so I'll fix them later. For now, reference the GitHub because I know that that one works. Okay, good on that. Structures. This is a good one. So we're going to have a structure for that IDT pointer. In the slides, this was the thing that's actually loaded into the LGDT register, or whatever it is, IDT register, limit and base. And then we have one for IDT entries. There's a char or char type, 8 bits. And at the end of these, we're going to have attribute packed, which is a really weird statement, I think, but it's another Mike Petch suggestion. And you can't forget the semicolon at the end either. Packed. And this is saying apparently the compiler likes to fill out these with 0 bits to the largest data type. In this case, like for IDT entry, short is the largest data type. So it would just use 16 bits for all of the fields, so it can quickly and easily look up the field without iterating through each. It can just multiply to get the memory address of the field, right? If 0 also takes up 16 bits, to get to 0, you just have to do the starting address of the entry times 16 times 3 or whatever. Or no, I'm sorry, plus 16 times 3 to get to 0. This packed attribute makes these actually take up 8 bits, which is what we want, because if we don't do that, it could get all misaligned because the CPU is not expecting them to be padded. So we want them packed. Good stuff. We've defined the structs. Now we need instances of these structs, or at least that's what I call it. Sorry if that's not C terminology, but I like to think of them as instances of the struct. This is our entire IDT, room for 256 interrupts, right? So it's just an array of these IDT entry objects. Cursor position equals 0. Before we go any further, lots of variables being defined here, very boring, sorry. Let's redo our main method. And I'm actually going to rename our main method to print message. So I like to change the character we're filling, changing it to a star. And I'm just going to change this to a nice general PKOS. And we're done. Our message is printed. But we definitely need a main method. So let's do void main. We're going to print our message. We're going to init our IDT. We're going to init our keyboard. And we'll enable interrupts. Would you look at that? We actually do need that. And then we're just going to do while one and forever do nothing in our main loop. And I think there's a more efficient way to do this, probably using halt commands or something along those lines, but for now I don't care. So we've defined print message. Next, let's do init IDT. And this is probably the biggest of the functions we'll have, but that's okay. We'll get through it one piece at a time. First of all, we'll have an unsigned int offset. That's going to point to our keyboard handler function. That's where that's coming from. Keyboard handler external void. This is referring to the assembly file, and we're casting that function to an unsigned int, which I think is pretty cool. So that's how we're getting the memory address of that function. And now we are going to set up our keyboard handler IDT entry. So we're going to go to IDT 0x21. And I was asking myself, why the heck is it 0x21? Well, if you look at 0x21, that's actually 33 in decimal. Recall that we have to leave the first 32 open for the CPU. I don't know if 0 is one of them. Maybe it starts at 1, and that's why we're on 33. Maybe we're just being safe. But either way, this is just out of range of those CPU interrupts that we're trying to avoid overlapping with. So that's where we'll put our keyboard interrupt. So the lower bits, we can just do a bitwise AND. The F's are all 1s, which means that we will, when we AND it, we only get those bits. You know, the zeros just turn into zeros. 0 and 0, 0, 0 and 1 is 0. So the selector is going to be our kernel code segment offset. That's 0x8 if you remember from up here. It's just telling us which entry in the GDT is our code selector. And I think that has to do with permissions and what ring you're in or something along those lines. 0 is just 0, that's for error checking. And if it's not clear already, we're filling out an IDT entry within our IDT entry table right here. The type attribute, we're going to set that to our interrupt gate 32-bit, another constant. IDT 0x21 offset upper bits equals offset and 0xFFFF0000, the upper bits. But we're not quite done yet. We have to right shift those 16 because when those 4 F's, you know, whatever's in these bits right here, when it is in that position, it's a pretty large number. It's also larger than the short type that we have here for the upper bits. So we have to shift it over so that we just get those and they're in the right position, if that makes any sense at all. Next, we can send our ICWs using I/O ports. So this is ICW1. We're going to reset both PICs by sending 0x11 to each of their command ports. I'll just mark it for now, ICW1, ICW2, vector offset. To the PIC1 data port, we'll be sending 0x20. This is our starting point for IRQ0. So the keyboard interrupt is IRQ1. 0x28 for PIC2. Makes sense. It's 8 after, I guess each pick has about 8 interrupts that it can handle. Cool. ICW3, we're going to say pick 1 data port 0x0, pick 2 data port 0x0. This is the cascading. This is how they're connected. Really don't know what I'm doing here, but I'm just going with examples I've seen. There's probably all kinds of fancy ways of setting that up, and then we'll use 0x1 for our environment info, and that's all we need to do to initialize picks. So we're going to mask all interrupts now. Why, I'm not entirely sure. I think maybe we mask all interrupts while we're setting things up, and then we unmask the keyboard one later. Next, we will load our IDT into the CPU so it can start using it. So we need to declare an IDT pointer, which is going to use this top data structure we have here, and we'll fill in the limit, which is size of struct IDT entry multiplied by the IDT size minus 1, always minus 1 by definition. And then we can just use the address of operator for the base. We'll get the address of the IDT array. And now we can use that assembly function we wrote, load IDT, and we'll pass it the address of the pointer that we just built, and we're done. What's next? We need keyboard init. What are we going to do for that? We are going to unmask the keyboard interrupt. So we'll say IO port out, pick 1 data port 0xFD. And just as a reminder, 0xFD is 1111 for F and 1101 for D. So if you think about IRQs being 0 based, then IRQ0 is represented by this one, IRQ1 is represented by this one, IRQ2 I guess is represented by this one. What we're doing here is unmasking. It's a 0 because it's not masked. We're unmasking IRQ1, which is de facto the keyboard interrupt. Finally, the real good stuff, the meat of it, we get to handle our keyboard interrupt. Remember that the IDT is pointing to the thing in assembly, which then calls this function. So now we can actually handle that interrupt. The next thing that we'll do is do an IO port out to the pick 1 command port, and we'll say 0x20. That is the end of interrupt command. So we can tell it, we're good, we've handled the interrupt, you can clear it out of your queue or whatever. Who knows what it does, but it wants to know that, we've handled the interrupt. So we did that. We can grab our status, which will be IO port in from the keyboard status port, which we defined at the top. So we can check the very bottom bit of the status byte that we just got. It's a byte because it's an unsigned character. So if we end that with 0x1 and it's equal to 1, then we know that we have a new key press that we have to handle. Given that you can check this using just the keyboard IO ports, I guess that's how they do it if you don't have interrupts. Because if you think about it, if there were no interrupts, we could just sit there in an infinite loop and check this status from the IO port. But we're doing it this way, and I like it. So there you go. Character key code. We're going to grab IO port in again from the keyboard data port. If key code is within range, if key code is not within range of our mapping that we defined in that other file, we'll get there in a second. In other words, if we don't have a character mapped for it already, we'll just ignore it for now. Otherwise, we will print character with ASM. We're going to go into our keyboard map included from the other file, grab that key code, print it in row 0, column, cursor position. Something handy is that it actually line wraps on its own. If you have a really large value for column, it'll just automatically continue to the next line, which is nice. And then we're just going to increment that global variable for cursor position. That is all for this file. And real quick, we can just create our keyboard map. I'm just going to paste mine in. Love copying and pasting. There it is. And what is this? It's just an array of characters. For each key code, it just gives you which character corresponds to that key code. That's it. Let's see if it works. Oof, I'm a little tired, and we have some compiler errors, some silly mistakes here. Let's get them done. I think my biggest problem here is the fact that I misspelled unsigned. Classic. Should be key code, not keyboard. I was dreaming. Okay, let's try again. Ah, there we go. It worked. And if we click in here and start typing, look at that. Wonderful. Feels like you earned it, huh? Never been so happy to be typing. And this should work on real hardware if you do the ISO. Classic typo, I forgot to make build debug a dependency of debug. Now for a fun but maybe not practical exercise, I didn't want to just take the keyboard map that people had on OS12. I was really curious as to how they figured that out, so I figured it out. If you do make debug, we're going to launch a GDB session on our QEMU system here, and you'll notice that nothing happens because we haven't started the system yet. That's what that TAC capital S, I believe, does on QEMU. It makes it stop beforehand, which is great because it lets us set things up a little bit. what we're going to do is set a breakpoint for number 77, line 77 in our code, which is right after we set that key code value to what we got from the keyboard. I'm really interested in what that key code value is, which is why I'm setting it right after it got set. So we're going to say break 77, and it worked, which is awesome. I'm going to type C to continue. Okay, cool. We don't have any breakpoints going off yet, right? Because there's no GDB prompt. I'm going to hit the J key on the keyboard. Take my word for it. And there we go. We hit the J key and we get a breakpoint. Everything is stopped now for QEMU. We'll go back into our GDB prompt. What can we do? Well, here we are. We're on our line that we wanted to stop on. We can print the value of a variable in memory, which is awesome. P/U means print as an unsigned integer. So we'll do that for key code. And that gives us 36. For your information, there are other things like P/X to print as hexadecimal. Let's go into our keyboard map and look it up and make sure that that's correct for J. So if we go to number 30 here, I tried to make comments so it's easy to look stuff up. 30 is A, 31 is S, 32, 33, 34, 35, and 36 is J. There you go. So yes, I really did go through, however many times and figure these out. There you go. Keyboard map done. Just repeat 60 times or however long. But yeah, fun stuff. That's how you debug using GDB. And you can just hit continue and it'll continue. You can hit another key, it'll stop again. Or just quit and get out of there. Quit, yes, there you go, done. So that was a doozy of a lesson. That was a big long one. And if you made it to the end, thanks a bunch. Hope you learned something. And we'll continue it next time.